All right, so it seems we are right on time. So hello, everyone. Thank you for joining for this STINT 2022 session. My name is Juan Fraire, and you will see my face around, I think, quite a bit these days. Yeah, so what I have prepared for today here is just very a quick slide as an overview of the agenda of the workshop that we are going to cover during this Wednesday, Thursday, and Friday. This is the agenda that is, of course, already published in the website of the STINT workshop. And basically, just some quick notes that for us to take into account. We are going to be using the same Zoom link for the 4 sessions that will host us together during these days. In all cases, the idea, as you see on your screen at the moment, is to record these presentations unless some speaker actually are against publishing them afterwards. We're going to make this available to people that want to, access the content in an asynchronous way. We are space networking guys, and we are delay tolerant, and we are asynchronous somehow. So we also kind of like to accommodate this type of communications. We have the idea of sometime in the future running stints in a way like mimicking if it is we're running an interplanetary environment, which is quite challenging. How would you run a conference in such a situation? So we are starting to get into that point. So what we have in today's agenda is we have our first keynote, which is, first of all, this session is going to be chaired by Scott Burley. I'm going to hand over to him in a few seconds. And yes, and our first keynote today is going to be Yosuke Kaneko from IPNSIG. He's already here with us. And we have 3 expert talks afterwards from Ronnie Bull and Mike Moore. Then we have Alberto Montilla from Spatium and Alan Hilton as well, that will share some of the recent updates on DTN research. And then we have also tomorrow, we have another keynote from ESA OPSAT operator David Evans, with quite a bunch of details of how this ESA CubeSat has actually provided a very interesting platform to evaluate some of the DTN experiment that some of the colleagues have been running. We also have some expert talks as well afterwards. And as well on the afternoon, we have another session with expert talks and some paper presentations, which are also shared with the YC conference, which this workshop is hosted as well within YC. So we are synchronized with them. You will see that these times that we have here in this agenda are also synchronized with the YC conference. So some of you might be jumping back and forth from the YC conference as well. At the end, on Friday, we have a series of very small, but quite possibly very interesting student talk, where we have different students that are working on related space networking topics to share ongoing efforts by different master theses and PhD theses and so on. Topics, of course, will be around mostly about networking applied to the space domain. And you will see some talks mostly focused on delay tolerant networking, the way of thinking on networking in the space context because of delays and disruptions. But we also have some talks like, for instance, Sandra Céspedes or Gunes Kurt, or Olivier Alfan, that will be also sharing some insights about IoT in space. We also share this asynchronous property with the rest of the protocols that we're studying in the other DTN domains. So unless there are any question, that of course you can use the chat if you want to drop any question there. I'm happy to be answering them asynchronously. I will pass the token to Scott so he can help us chairing the session of today. So thank you for joining, and Scott, the floor is yours.
Sure. Thank you, Juan. And on the questions, because these topics are all the talks are going to be quite brief, we don't have a lot of time to spend many minutes on questions. So the ideal thing is perhaps to ask a question in the chat. We may be able to talk about it briefly at the end of each presenter's talk, but follow up with email. I think there are detailed discussions that are needed. That said, let me just introduce our keynote speaker, Yosuke Kaneko, who is at the Japanese National Space Agency, JAXA, and is the chair of the Interplanetary Networking Special Interest Group, which is now the interplanetary chapter of the Internet Society. Kaneko, please go ahead.
Okay, thank you, Scott, for the kind introduction. So let me start sharing my screen over here. Okay, do you guys see it?
Perfect.
Okay, very good. So I'm, again, Yosuke Kaneko, and I would really like to start by thanking STINT for inviting me to this event today. It's basically my first participation in the STINT workshop, but I'm really happy to share our activities at the IPN-SIG and some work and progress done at the Architecture and Governance Working Group. So I would like to kind of, start by, okay, here we go. So I want to kind of start by talking a little bit about ourselves. Some of you may be already familiar with the IPN-SIG, but we are a US nonprofit organization working towards to expand networking to interplanetary space for the benefit of humanity. And along these lines, the IPN-SIG is working toward to create a common vision of an interplanetary network with the various stakeholders, and to offer a narrative and a roadmap that would enable the development and evolution of the interplanetary network. And also to promote the use of the DTN protocol, which is one of the critical technologies to conduct communications at interplanetary distances. And the IPN-SIG logo that you see here really represents our goals and vision. And this logo was designed by Juan, especially designed by Juan, and he's done such a beautiful job. So thanks again to Juan. We really love this and really use this everywhere. Okay, so before I kind of start talking about what we're doing here at the IPN-SIG, I want to kind of really start with where we are today. We have, several space missions going to the moon, Mars, and farther beyond to other planets and also to asteroids. But communication is basically done in a point-to-point fashion. We talk to a given spacecraft to control it and get the data down. So basically, it's simply as that. But when we put our eyes around the globe, what we're really seeing here is that many of the industry and nations are providing significant efforts in space communications. This includes the NASA's LunaNet program, driven by the Artemis program, and also the ESA's Moonlight program that allows for human and robotic exploration on the moon. And there are lots of industry players supporting these programs. So more industry, more nations are coming into play and are bringing in their concepts into space. So there's a huge amount of thrust that's really pushing the horizon of space communications today. And kind of fast forwarding a little bit to the 2050s, I love talking about this. We might have a commercial space station in low Earth orbit, a lunar base, and perhaps a Mars base, and several spacecrafts orbiting the moon and Mars. So it's conceivable that we might have an Earth, lunar, Mars network backbone supporting the various activities in each planetary domain. And then going even farther in the 2100s, we might even end up in a picture like this. This is a notional picture that was crafted a little while ago, but it gives you a sense of what a solar system internet, or what we call the SSI, would look like. The red hexagon lines in the middle of the picture is an illustration of a network backbone of the SSI relaying data across our solar system and even for deep space missions. This is really not the solar system internet that we might be building, but what IPN-SIG envisions is a common network backbone that enables science and exploration and commercial activities, and could even support our normal daily lives. So the solar system internet is rather like a concept of networking the planets, or networking the things and humans at an interplanetary scale. So that's what we've envisioned on how the SSI network might scale over time. And then we kind of started to ask ourselves, what might be the issues that confronts us in order to realize such an infrastructure? What are the lessons we can learn from the evolution of the internet? Or how could the SSI evolve over time, considering the various players in the space arena today? Or what are the key properties that might support a common solar system internet? So in order to give a thought to these questions, a group called the strategy group was formulated, and Vint Cerf and also Scott Burley was also on the team. And after we had a lot of discussions, we did publicize a report last year titled The Strategy Toward a Solar System Internet for Humanity. And I will kind of try to touch a little bit on what we said in that report. So first, we try to look toward the future on how the solar system internet architecture could change over time. And here's what we said that might possibly happen. If you go to the left-hand side today, the government and the space agencies have developed and sustained a network backbone in space, and some of the commercial users are using that infrastructure. This is where we are today. But maybe in the next 30 years from now, some people say that this might come much earlier, but the architecture could evolve to a state where government and commercial and academic backbones coexist and even have the capability of interconnecting them together, similar to the peering concept in the internet environment. And even in 100 years from now, we may have a commercial sector primarily running their own backbones to serve multiple users. But we also think that there still might be a dedicated backbone serving for government and also for academic purposes. And then, and then we kind of started to ask ourselves, what are the significant properties or the principles we need to pay attention to in order to support that evolution? So we've kind of pondered upon ourselves and laid out 7 key properties. So starting with collaboration. Yes, of course, we need collaboration to realize an SSI. The IPN6 sees the solar system internet as a common structure for all humankind. And we should try to build it as a common system, understanding that investments made by various players today will become mutually beneficial in the long term. And then global standards. Having a unified global standard is crucial to establish an SSI. This is no need to say, but if you look at the internet, we had the TCP/IP or the BGP, and these showcase a single way of doing things. So that was a very successful case. A single technical standard that's open and free and accessible for everyone is really the key to make SSI a reality. And the other thing is that if we have a good standard, it also enables innovation. Stability. Yeah, this part was intended to have a tie with the standards part, where we should avoid having standards rapidly changing or not becoming backward compatible. So stability of a standard is important to sustain the robustness of the SSI architecture. And we also said democracy. We should also accept the concept of a democratic approach to construct the solar system internet, which basically means that any entity who would wish to join the SSI would have the freedom of doing that. No single actor should direct configurations for the SSI, and the SSI should naturally evolve. However, we should accept minimum governance required to preserve the coherence of the overall architecture. The next piece would be affordability. The SSI must be affordable to its users. Affordability is a key aspect, but it could have a different meaning to each of the stakeholders. For instance, for a commercial entity, it is important that the development cost of a given product will need to be recovered, perhaps by providing networking services or something. And for an academic entity, the costs incurred to use a network must balance with the expected science outcomes produced. So the term affordability does not necessarily mean cheap, but rather the costs incurred must be paid for. And then last but not least, security. Maybe I skipped one. Expandability. Yeah, sure. Expandability to scale up and add new functionalities to the network. It's important. It's also important to note that flexibility in architecture enables expandability. So both pieces are important. And then talking about security, yes, we've already talked about the democratic approach of allowing freedom to join, but at the same time, it's also critical that the architecture is capable of securing information that it carries for safe and secure use of the network. So we should keep our eyes on the democratic side and also on the security side. So those are the 7 key properties we have laid out so far, which might support the development of the common solar system internet. So again, the IPN-SIG really believes that SSI should be built as a common structure. Having a common structure will lead to sustainable and resilient human activity, and a common infrastructure would lead to driving innovation as well. And we believe the very first step is to come up with a shared vision toward a common SSI and recognize the value it creates. We also think that the concept of co-creation with the public and private sector is also indispensable. And if we are successful with that, we should naturally end up in a coherent SSI architecture. And here I would like to touch upon some of the initial steps that we have laid out toward the realization of an SSI. These are some activities that the IPN-SIG proposed in the strategy report in order to make progress in the near term. The first pillar is about testing DTN at scale. What we're hoping to do is to have a DTN embedded in some terrestrial system to create a significant amount of traffic on Earth to test the overall performance of the DTN protocol. This is kind of an effort that would enable us to refine the technology to adopt it to a more scaled SSI network. And then the second pillar is to test interoperability between the various implementations of the DTN protocol. A third pillar is about promoting DTN. We believe by increasing the exposure of this technology will contribute to more investment and adoption of this technology to operational implementations. One of the success stories of the internet's evolution was the founding of the Interop exhibition. So it might make sense to explore setting up a similar exhibition to draw more attention from the government and the commercial sector. So that was the third part. The fourth pillar is about deploying experimental and active missions to demonstrate DTN in space. And the fifth pillar is to explore a well-functioning and healthy governance model that would support the development and evolution of the SSI. That's exactly why IPN-SIG has set up the architecture and governance working group, which I will talk about in a moment. And of course, our sixth pillar is to instill our vision and conveying it to our future generations. And this year, we have successfully started the IPN-SIG Academy program, which delivers a series of talks for the younger generations who would be promoting the work of the SSI. And I will be touching on this a bit more on this later on. So the Architecture and Governance Working Group, or the AWG. We have established this working group early this year, mainly focusing on the two aspects that you see here. One is to explore the desirable properties of a common SSI architecture. Some of the questions we would like to tackle is how could the various networks, such as the public or the academic or the private sectors, work as a whole, interoperate and work as a whole network? Or how could the cellular network coexist with the SSI? And that will be the first piece. And then the second part is to assess the management design to realize a common SSI. The point here is that the SSI could be made up of multiple and independent but interconnected networks that requires collaboration. So some of the questions we raised and try to answer is what institutions and governance practices would need to be employed to support this level of complexity? Or how will administrative responsibilities be discharged fairly and also reliably? So these are the kind of questions that we've been trying to tackle at this working group. So here's our members list of the AWG. I'm not going to read this whole thing out, but so far we have 10 IPNSIG members on the left-hand side, including Vint and also Scott Burley. And on the right-hand side, we have invited members. Dr. Scott Pace is on the team from George Washington University, and many from the space agencies like NASA and ESA and JAXA are also contributing to this activity. So you may be wondering why governance is a theme today. You know, first and foremost, having a common SSI infrastructure enables sustainable and resilient activities in space, and it also allows for innovation. So number one, working toward a common SSI, that's the way to go. Secondly, the build of the SSI is really starting with the NASA's LunaNet and ESA's Moonlight programs. Humans will start building infrastructure around the moon and onto Mars. And we've already kind of entered the prologue of the development of the SSI. And thirdly, this is an important piece. Thirdly, we must take into account the lessons from the internet. History has told us that the internet had took the path of technology first and governance after. The emerging technology that gave birth from the ARPANET project has become so foundational to our lives over the course of time. But the management or governance of the internet system had to be sought after the spread of the technology. So I kind of view this as as internet was kind of responsive to what had occurred. So we want to kind of learn from this. So for the SSI, we want to try and attempt to do governance from the beginning, and I think that's an important message here. Because good technology and good governance model is the key in realizing a common SSI. So I just talked about why governance is important, but the next question would be, what do we need to manage? So far, the AWG has identified a few of them already. We are still having ongoing discussions on this, but this is kind of a snapshot of today. No need to say, but critical resources that has limits in their resources, such as node numbers and spectrum, and maybe sometimes IP addresses are items that needs to be managed. And network connectivity information. In the SSI, we're not going to have 24/7 connectivity like the internet. So the users of the SSI network will most likely need to schedule a data transmission or create a plan prior to sending any data to its destination. So in order to accomplish such planning, we need information like for when and for what duration and in which bandwidth will I get my next path, or where's that information stored anyhow. So the collection of this information needs to be available and accessible to its users, which is very critical to make this infrastructure operational. And of course, standards, communication standards, time standards, these are things to be managed. And norms and procedures required to support the governance practices. These are important pieces as well. And here, I would like to show you what we have come to put together on the recommended approach on SSI governance. This is still a snapshot. This is why I have draft on the top here. But this is what we said so far. It's mainly in 4 areas that you see here. First is to design for open access, which allows freedom in the governance model. Second, governance at the right levels. Some management can be undertaken by an international organization, and some could be undertaken by the private sectors. So governance at the right level is a very important piece. And distribution of control, which would be a concept that enables governance to be distributed among stakeholders where possible. And lastly, for the long-term sustainability of the SSI, employing a multi-stakeholder approach is important as well. And I think the internet worked very well employing this concept. And let's see, let's go to the next page. So that's how, that's basically how far we've gotten at the working group. And our next steps at the working group is to assess how could we collaborate to manage them. In the internet, there are various entities that support the internet, like ISOC and ICANN and regional registries and many other forums. And they also have their roles of sustaining the governance of the internet. And what about the SSI? We have the CCSDS and of course the space agencies and many other groups and forums. And of course, STINT is a fantastic venue to promote the DTN technology. So what we're trying to do at the working group is to analyze the internet versus the SSI models and each organization's roles and kind of offer some kind of recommendation on how all these organizations could collaborate toward realizing a common SSI. Once we have something to show to everybody, our plan is to share it with our external stakeholders and further refine it together. I am kind of running out of time, so I will kind of move fast. So I just want to take a moment to briefly touch upon our recent program called the IPN-SIG Academy. We have a long way to go to realize SSI. We have another 100 years to go. So our generation alone cannot achieve this goal. So that's why we've set up this IPN-SIG Academy. It's basically a venue to kind of nurture the knowledge and expertise for the young generations who would eventually become the real engines of making this real. So we have kind of laid out a variety of talks by the most prestigious people around the globe. We are kind of halfway through the program, but we still have a lot of exciting talks to go. Actually, we have a NASA LunaNet talk tomorrow from NASA. So if you haven't signed up for it, and if you're interested, make sure you sign up for this as well. And then lastly, maybe a couple more, but a quick announcement on our 100 Years Promotion video contest. We're currently looking for a graphic designer who's willing to showcase our vision and mission in a short video format. Anyone can join the contest, and we're planning to provide a modest amount of award to the winner. So if you're willing to be a part of this, you're most welcome. So please come and visit us on our website to find out more. Okay, and just a one-pager intro on the working group activities. I did not speak about the projects work we have at the IPN-SIG. Projects are handled at the PWG, the far right box up here. And basically in the PWG, we pursue many projects to refine the DTN technologies. And if you're interested, please come and check our website. And I think Oscar would be delivering some presentation at the STINT, so I think he may have more information about this. And if you want to become a member, just shoot us an email to membership@ipnsig.org. We got, I think, 890 members right now, so it's still growing. Okay, and I promise to stop here. This is my last chart, but I'd like to conclude my presentation by showing you our new interplanetary chapter logo of the Internet Society. And that concludes my presentation. So thank you very much for your attention.
Okay, thank you, Kaneko. I'm sure that a lot of people are going to have questions about this. As Juan has pointed out in the chat, it'd be good to type those questions into the chat and or follow up in email afterwards, and we should move on now immediately to the first of our expert talks. Let me just bring up a little biographical information here. This will be our first talk will be from Ronnie Bull and Mike Moore of Adirondack IT Solutions. Ronnie is the owner and chief scientist of the company. Mike is the chief engineer, and both are active in many other activities of the DTN community. And I will stop introducing at that point and turn it over to Ronnie and Mike.
I think, Kaneko, you need to stop sharing so that Ronnie and Mike can take over. Thank you. Mike, if you're talking, I think we're not hearing you.
It sounds better.
You guys hear me?
Yes.
Yeah, excellent.
My machine crashed on me. Are we ready to go? I apologize.
Yeah, please go ahead.
Okay. Looks like Mike is sharing the slides here, so I'll just let him go with it. So thank you for the opportunity for us to be able to present our research today. We're from Adirondack IT Solutions. We have a NASA 2022 SBIR Phase 1 effort. It's a 6-month period of performance from January 25th to or July 25th to January 25th. Next slide, please.
If you want to go into slideshow mode, that would be better so we can see the full screen.
So we are Adirondack IT Solutions. Like I said, we are located in central New York, right pretty much smack dab in the center of New York here. We provide IT consulting, networking, computer systems engineering, security auditing, custom software engineering services for different organizations, schools, local governments, Department of Defense. So that's just a general bit about us. Next slide, please. So for this team, we put together a pretty solid team of engineers, networking, emulation experts, as well as a few consultants. Scott Burley's on there for ION expert and reactive routing development. We have Joel Seif, who's also working with us as a consultant for documentation and commercialization plan. Mike Moore, who you're going to hear from next, is the chief engineer and the primary investigator on the project for NASA. I'm the point of contact. And then we have John, David, and Joshua, who are working hard on our emulation platform and integration. Okay, Mike, if you want to take it from here.
Yeah, from the chat, it looks like Mike's having some problems with audio in his browser.
Okay. Well, Mike, do you want to move on to the next slide? Sorry about the complications here, folks. We're soon having Zoom issues.
There we go.
You able to talk now, Mike?
I think Mike is not looking at the, may not, oh no, he was in the chat before. I don't know.
Yeah, the rest of the presentation is him. So let's let me give him a call here quick. Make sure that he's able to do the audio. Basically, this is from the solicitation. We did apply to the cognitive communication subtopic, which focuses on space communication driven by onboard data processing, modern space networking capabilities. So our goal is really to improve the communication efficiency, mitigate the impairments, look at the physical layer, what's coming through the physical layer in terms of the radios, and gather data based upon the communication channels and make intelligent decisions in order to route traffic and forward traffic based on that. This is Mike trying to call me right now. Hold on a second. Okay, the rest of the talk is going to be Mike. He's going to try to close his browser and come back in to fix his audio issue. But I will start sharing the screen so he doesn't have to worry about that.
Yeah, good idea.
So while we're waiting for him, we developed a roadmap or a vision of how we think that SDR in space should be in the next 10 years. We're looking at software-defined radios. We're looking at how these are going to develop over the next 10 years. And we kind of laid out a vision of how we think we should be able to move forward into autonomous networking within DTN networks. So we have basic contact graph routing here at the start of our roadmap. Currently, we're here trying to integrate reactive routing. And then after that, we're seeing region forwarding. This gets into Scott's ideas of regions in terms of how the IPN is going to be laid out going forward. Flexible modems. These are modems that are actually able to be controlled by software, be changed by software down the road, updated. Then we go into opportunistic, supposed to be routing, where we're looking at information based upon our radios, what we're getting from the physical layer, the information on bandwidth, if you know, a link is better characterized than the other one, if we have better metrics for one over the other, and basing our routing on that opportunistic. Or maybe this could even be nearest neighbor. So maybe we have a spaceship coming into contact with us, or a satellite that's a fairly close peer to us that we can convert over to using that link. That might be a better opportunistic route for us than the current link we're using. This also brings us into beam steering, which down the road we're able to control the way the beams when we start getting better radios, where we're actually able to direct beams out to other systems or nodes on the network. We're able to control those beams and steer them so that we can actually control our radio focus. Multicasting, and then finally fully autonomous networking. So did Mike jump back in yet? Looks like he is in, and it looks like he has audio. Mike, can you take over now, or? Slideshow mode. Is that better for the slideshow mode? I don't think my screen sharing is working too well on. Okay, still no audio from Mike, so I'll just keep going on with our basic slides here. So the advantage of software-defined radios, we have significant development cost reduction. We're able to do software changes on these radios as we need to push updates down them, so they do have flexible waveforms. We can do cognitive radio with these ASMs, we're calling them. We can also configure dynamically scheduled configurations and push them up as we need them to change them on the fly. It's more than just a digital radio, so we can actually promote spectrum sharing. We can have different efficiencies and waveforms, and we can have dynamic adaptation down the road for interoperability. So if we want to actually put in different modules, work with different types of protocols, we can do that through software. So there are standardizations. There is this EDA, ETSI military SDR standardization, as well as VITA 49. So these are standards that are already required for optimal utilization of the software-defined radios. We're looking for further standardization in terms of how these are going to be used in space, which is going to be important to our future research in this area. Okay, so as features become more advanced, it's going to actually drive computation capability and commercialization. We're seeing high-performance computing processors being developed on very, very small microcomputers now. So the processing capabilities that are going to be on satellites in space in the future is going to be very vast. Looks like Mike's actually got something going on there. So here we can see control state and metadata are increasingly feature packed as waveforms become more advanced. So as we can get more information from these waveforms, we're going to have to be able to pack this metadata with more information. Mike, are you able to talk now?
Can you hear me?
We can.
Hello?
I will let you. Yeah, I will let you take it from the slide.
Excellent.
Okay. I hope I can pick it up in the stream here. So our focus has been on what we can do with software radio to facilitate things in DTN. And okay, I missed half of your talk, so I'm just going to start with this slide. There's a lot of control that can potentially go on between the software radio and the network layers above. What we're envisioning is that future software radios will have a fairly large waveform library. It's the various waveforms can do things like carry more information, security, just private protocols. We also are thinking about link control, what radios can do with that, and in particular, the pointing and security, spectrum sensing and perception. So this leads into cognitive radio. Cognitive radio has not been interacting on the network levels. It's been giving a spectrum capability to the endpoint, to the receivers, and we think we can use the network maybe to work with cognitive radio or put the cognitive portions of the radio up in the network to optimize network layer things and try to simplify network operations. One of the reasons we think we're going to have very capable software radios is the compute platform that the software radios are on are headed towards much higher performance. At present, what we're seeing is essentially FPGAs, but there are multi-core solutions out there that are true software platforms that can host a fairly high throughput capability with a radio and provide a great deal of flexibility with waveform at the same time. Next slide, Rennie. So our first step is reactive routing. We're going to take a look at what DTN can use from the tool set that a radio could possibly provide to DTN. And for that, we started out with sort of a vision of what a software radio might be able to provide in about 10 years. Just sort of a guess based upon what we've seen happening. And we're going to be doing some experiments to see what parameters in particular can be used to facilitate DTN improvements in performance and simplicity of use. So that ends the technical portion, and looking for questions.
Thanks, Mike. I'm looking on the chat, and the questions so far have been really about the availability of the slides. So I think I'm not seeing any technical questions right now. Anybody that's got anything to bring up at this point, unmute yourself and say something, or write something in the chat. And if not, then we'll press on to the next talk. Oh, okay. So there's one question here from Juan. Can you comment on what specific feature of contact graph routing will be mapped to the software-defined radio?
We're looking at several features of, several parameters that a software-defined radio can provide. One of these might be forward error correction information. When you receive a transmission block, you will most likely do some kind of forward error correction. And the number of bits that are corrected is kind of a measure of how noisy things are. It's similar to signal noise ratio. If that number of bits that are being corrected starts approaching the capacity of forward error correction, it might be time to signal the use of a different modulation, or a different, or possibly maybe a different carrier frequency. There are other things involved there too, like possibly background noise, or how busy the channel is. It's a cognitive radio might provide information about congestion that's going on. So we're going to be looking at probably 2 or 3 parameters at a time. Do some simulation work to see what kind of improvements we can get.
And Samograsic asks what kind of hardware will be used for this work, and is it going to be custom hardware, or will it be open specifications, open source software?
So I think you're asking about the radio itself, what kind of software radio?
I think really what the platform will be for these adaptations. For example, I know there's a high performance computing platform that NASA has been developing. What's the is there a hardware target for this work?
There's no specific target. I think that the computing platform in question here is probably whatever is hosting the radio, because the radio is going to make some very high demands on whatever platform it has for throughput. We are not targeting a specific radio, but we are
okay.
Yeah.
Okay, and go ahead.
We're targeting characteristics. So we feel that we can eventually provide guidelines for what characteristics a radio should have to support a DTN.
So would these be, is there a place for FPGA in this architecture, or are you looking really at multi-core processors more?
We're agnostic about the platform. We're assuming it's going to have enough throughput to host probably maybe a gigahertz, gigabit or better platform. So we're probably talking, I think it's S-band utilization here. So if we can support that amount of throughput with a variety of waveforms, we don't care what the platform is. So we're making assumptions that in about 10 years, we're going to have some rather capable radios. And rather than whether that happens on an FPGA platform or a multi-core platform, we don't care, as long as the system exhibits the characteristics that we need. I think what might happen is that if we find an interesting characteristic that's particularly difficult for an FPGA, that will just kind of drive towards multi-core a little bit more. And whether multi-core will actually make it is not a given at the moment. There are advanced platforms being evaluated, and if those are successful, then I think that the economics will make them the pick for the radios over the FPGAs.
Okay, and I think that brings us to the end of this 20-minute slot. So if there are more questions, please go ahead and enter them in the chat, and Mike may be able to respond offline. And now we should move on to our next talk, which will be Alberto Montilla, speaking for Spatiam Corporation. Alberto is co-founder and chief executive officer of Spatiam. He's also a board member of the of IPN-SIG, and his son Alberto Jr. is co-founder and is the technical lead at Spatiam. And with that, Alberto, can you go ahead and start sharing your slides?
Thanks, Scott. Can you see my slides?
I see them, yeah.
Thank you, and good day, everyone. And thanks. So we, Spatiam Corporation, we're a startup aiming to contribute to the creation of the interplanetary internet.
Excuse me, Alberto, there's some sort of grating or scraping noise in the background. Is there an open mic somewhere, maybe?
Is it better now?
Yeah, that's fine.
Awesome. So I was saying that we're a startup aiming to contribute to the creation of the interplanetary internet through our DTN platform. And today, together with Alberto Jr., we're going to be talking about the application interoperability test that we performed between ION and micro DTN bundle protocol version 7 implementations. Before we go there, a quick recap of what's Spatiam's DTN platform. Our main goal is to deliver operational DTN networks that basically where multi-administration as well as multi-implementation is present. These are two critical elements of an open interplanetary internet. So that's part of our operationalization goals. And with the platform, we're able to create and manage DTN network overlays, ideally open between agencies and commercial nodes. We're able to deploy managed DTN instances for both space and ground operations for forwarding and transfer of data. And the platform is integrated or can be integrated with mission operations through APIs, for example, for contact plan scaling. As part of the product portfolio, there are three main elements. The first one is the DTN manager. It is basically the construct of the DTN network overlays to manage the overlays, the contact plans, as well as manage the DTN nodes. Then the DTN managed instances, which basically are the nodes, the DTN nodes that host the bundle protocol for forwarding bundles. And then the DTN node CLI that, as the name indicates, provides a remote access to a command line interface for low-level operations in each of the nodes. I want to highlight that parts of the DTN platform, more specifically the DTN manager, is being used by the IPN-SIG pilot project network. And for those that doesn't know the network, this is probably the largest known agency network out there. It has more than 20 nodes, actually very close to 30 nodes, and more than 12 distinct administrators that are spread around the world. And the DTN manager is used as a node registry, and of course, as the manager of the DTN nodes that Spatiam contributes to the network. So let me talk about the motivation of the interoperability tests. As many of you might know, in May of last year, we performed the first commercial DTN interoperability test in LEO. That's thanks to the collaboration. We basically were collaborating with D3TN, which had the main interface with the European Space Agency experiment using the OPSAT small sat. During that experiment, we were able to perform interoperability tests at the core bundle protocol level. What that means is that ION, as you see on the screen, the ION node that we were providing was sitting between two micro DTN nodes or many micro DTN nodes, but the applications were always interfacing micro DTN nodes. At that time, due to the time to perform the experiment, we couldn't test end-to-end application interoperability between ION on one end and micro DTN on another end. However, having said that, the tests were very successful, thanks to the help of IPNC as well as Lara Suzuki from Google. We were even able to test a cloud vision application through DTN, emulating the ring road network through the ESA OPSAT. So we wanted to extend those tests where ION was not only in between two micro DTN nodes, but ION was in at one of the ends, and see how the applications could work together. The second main motivation was we wanted to add micro DTN nodes into the IPNC network. Till then, at that time, the network had around 20 nodes. Till then, all the nodes were based on the ION implementation, as one of the goals of the IPNC is to build an open network, supporting multiple implementations was a critical objective. So with that being said, we set the following goals for these interoperability tests. The first one is we wanted to determine the configuration parameters to connect ION and micro DTN nodes together. And that's, again, extending the findings of the OPSAT experiments, considering that now micro DTN supports, in addition to the DTN scheme, it also supports the IPN naming scheme, making things a little bit easier. The second one was to update the generation of the network parameters to support micro DTN nodes in Spatiams in our DTN manager. And the third one was to test the interoperability between ION and micro DTN applications. So with that being said, I'm going to pass it to Alberto Jr., who's going to go through the configuration and the results. Alberto?
Thanks, Alberto. So with this part of this presentation, I would like to introduce some key technical aspects of the tests we ran, starting with the configuration of the nodes in the network. So for these tests, a very simple 2-node network was created. The bundle protocol version used was the latest version 7. And as Senior mentioned, MicroDTN recently began supporting the IPN scheme. And as ION already supported it, this was the node ID scheme used. And the TCP convergence layer was used as both ION and MicroDTN supported. Now, both implementations are set up in similar fashions. Nodes are built and then configured with a series of commands. For ION nodes, these commands can be packed into one single configuration file that feeds the different admin processes information about the node and the network. In ION, to add a contact with a MicroDTN node, the most important part are the commands that you can see on the screen, which tell the bundle protocol and IPN admins to add a TCP outduct to the MicroDTN node and associate this outduct with the node, in this case with IPN 200 for MicroDTN. So in MicroDTN, once the node is built, new contexts are added via a configuration endpoint, and this can be accessed by the AAP config command in order to specify the address of node 100, the start and stop times of the contact with the ION node, and the link's data rate. Now, knowing how the configuration process functions, we extended these commands to be supported in the Spatiam DTN manager. So our goal to support multiple bundle protocol implementations in the manager began with letting users choose between the LTP and TCP convergence layers. The TCP convergence layer is the newest convergence layer supported. So therefore, MicroDTN nodes could be added into the network, since at the time this was the supported convergence layer for the implementation. This way, since the manager allows users to download ION configuration files that set up the ION nodes, the manager has a process that lets you generate and download this configuration file. So for this reason and node creation, users are now asked to define the implementation used by the node. So this configuration can be accessed accordingly. With this, users can declare both ION and MicroDTN nodes, and ION users can use the available configuration file to set up their nodes. Next slide, please. Thank you. So both ION and MicroDTN come with a predefined set of applications, and these are used to send and receive string payloads, echo and ping messages, files, and more. For MicroDTN, these applications use the application agent protocol. And for practical purposes, we focused this interoperability test on messaging applications to send and receive string payloads and the echo bundles. Our goal is in future iterations of this interoperability test to focus on file transfer and other capabilities between the two implementations. Now to set up the test for the first round of internal testing, we set up a network with 2 nodes in our internal cloud, and the initial test ran successfully. So we proceeded to create a new overlay in the DTN manager and declared an IO node managed by us at Spatium. Then D3TN proceeded to host a micro DTN node and declared into the DTN manager as well. For us, we used the generated configuration file from the manager, and D3TN manually added their contacts to our node. So what were the results of the final experiments? In general, the applications that forward and receive string messages were able to communicate across implementation successfully, meaning that ION's BP trace application was able to send messages to micro D3TN's AAP receive, and micro DTN's sending application, which is AAP send, was able to communicate with ION's BP sync. Now, we also tested the ION's BP source application and found it to be interoperable with micro DTN's listener. However, BP source and BP trace are different in the sense that BP source does not specify a bundle origin on its payload. So AAP receive will log a message received by micro DTN. However, the source of the bundles will be DTN none. So we essentially discovered that BP trace would be the preferred string payload application to be used. And lastly, the newly implemented micro DTN applications to send and receive pings were compatible with IONS. So now we have the ability to monitor connections and have persistence logging between implementations to have updated information about nodes being able to communicate with each other by perhaps running these applications in the background. So we would like to acknowledge the D3TN team for their support in making this test possible and integrating micro DTN in the IPN-SIG network. We see this as a major step towards an open DTN network. Also, I would like to thank Oscar Garcia and the entire IPN-SIG pilot projects working group for contributing to making this happen. And with this, we have come to the end of the presentation. So thank you very much.
Thank you, guys. I see 2 questions in the chat room. First, do you plan to support UDP convergence layer adapters as well as LTP and TCP in the configuration platform that you've got going in the near future?
So I'll take this one. The short answer is yes. As you may imagine, we are expanding into supporting convergence layers and implementations in general. So we're going step by step, looking at the different needs of the current application. So for example, we have been focusing on enabling the IPN-SIG network. As we find, the need to provide other CLIs, we will do so. It's the construct is pretty much the same, so it's not a large effort. It's more about finding the right project to basically right motivation or justification to do it.
Thanks. And then one other question from Stuart Card. He asks about there's a skips TP variant on TCP, which is a performance enhancing proxy implementation, and there's also a norm multicast based protocol that runs over UDP. Have you thought about supporting those convergence layer protocols in future editions of the software?
Yes, in general, but we will need to have, specifically to these two, we will need to have, a specific, implementation or application to go this route. Considering that, right now we are using ION as well as micro DTN, and in the future, we are thinking about implementing things like HDTN and the likes. We will need to see, what is the specific application requiring these. When I say application, the specific network setup requiring these, and if there is, so we will, we would love to do it. As I said before, it's not an extraordinarily large effort, but you know, it's a question of priorities right now.
Sure. Okay. I think that is the last of the questions I see in the chat. So I would propose that we move ahead to our last expert talk, which would be Alan Hilton. Alan, are you ready, or do you need another couple of minutes?
Hey, I think I'm ready to go.
Oh, okay. Let me do a brief introduction then. Alan has been on the DTN team and in the community since 2009. He's the energy behind the HDTN implementation of bundle protocol at Glenn Research Center. And let me see if there's anything else I should bring up here. I think that's probably enough for me to say right now. I should let Alan go ahead and start talking. Please, Alan, proceed.
Thank you, Scott. Can you guys hear and see at least my slides?
Yep, perfectly.
Yep.
Awesome. All right, thanks, guys. Yeah, I'm Alan, and I work up at NASA Goddard. I used to work at Glenn, where I did a lot of DTN research, and now I'm still trying to keep that alive, but I'm moving on towards other things I'll talk about here. So I'll begin by talking about DTN and the Near Space Network. So the Near Space Network is our global communications network at NASA that basically takes us from the surface of the Earth to the moon. And then we're complemented by our wise and powerful colleagues at JPL who take care of the deep space network from the moon and on. And these days I support the NSN as a manager, and I am more or less responsible trying to figure out how we are going to integrate DTN as an NSN service. So that's really the focus behind pretty much everything that I do these days. Towards this is LCRD, is our laser comm relay demo satellite that's launched almost a year ago, and will provide fast link. It's about 1.2 gigabits per second. It's a slow link. It has a 4-second round trip time, and it takes us either from optical ground stations, other optical ground stations on the Earth, or perhaps from such LEO satellites as this thing over here on the left to the ground. And for me and for us, it's also a platform that will enable greater scales and speeds, and also integration paths for DTN. And I'll talk a little bit about that, but I'll kind of move forward to Illuma-T, which will complement LCRD. So if we have these optical ground stations on the ground, and of course this is to scale, they're bigger than they look, would go up to this optical ground or optical satellite, LCRD and GEO, which could talk to Illuma-T, which is an optical terminal that will be bolted to the space station. And as you may be aware, there's an existing DTN aboard the space station. Has been consistently since I think 2016. Somebody can correct me in the comments if I'm wrong. I know it got started around 2013. And so this represents a growing network, both in terms of speeds and capabilities. We're looking at multi-gigabit per second links, but also in terms of having hops and paths. Not shown in terms of paths would be, of course, this doesn't replace any extant RF paths to the ground. And then as we grow from here, so this is something that we're going to be looking for in the next calendar year, really. If all works well, Illuma-T will be launching in February, and we can start to move forward with it. And then, as I brought up early in the morning, this will give us a path towards the so-called LunaNet, which, as shown here, really is a multi-hop, multi-path, far-reaching network that shows a great heterogeneity in assets and capabilities and so forth. And so this is essentially my goal, is to find a way to put DTN on all this stuff to make it a reality. And there are a few steps that we need to take towards this implementation. So I'll talk about an old test that we did about a year and a month or so ago up at Glen, where we had a free space optical link, that is to say, no optical tethers from the aircraft to the ground, about a gigabit per second, sending roughly 34 gigabytes of file data per test over a variety of convergence layers. And this was great. You could do it with and without custody. We were always able to saturate the link. And then, of course, the next thing we want to do is take this forward. And I'm going to start doing this on LCRD for ground station to ground station comm. And we've heard a little bit about HDTN. There's also the DTN Marshall Enterprise, and these two more or less represent NASA's high rate DTN endeavors. Because of our 4-second round trip time, it'll be LTP only, but the goal will remain the same. We want to saturate a gigabit per second pipe with bundles, where the bundles can be of essentially any size. Where right now we're seeing there's kind of no issue pushing gigabit rates with bundles of about 7 or 8K in size. And then I can try playing with it in a variety of ways, either BPv6 or v7, with or without custody, with and without BPsec. And in particular, HDTN and DTN use OpenSSL for BPsec, which has been pretty fast. And I'm grateful we don't have to implement all of those things. And this is really all about some of the technology. Like I want to run this DTN instance and I want to connect it to this satellite, and I'm going to flow bundles like this. There's other sides of it as well, which are kind of more programmatic. I love this picture just to show how much lasers love clouds. But the LCRD ground infrastructure and also just the NSN infrastructure in general is becoming more and more cloud-based all the time. And so rather than having DTN gateways at the ground, we would just look to have DTN instances in some government cloud to make it easier for internal, but also external and even foreign entities to connect to do everything from conducting LCRD tests to working with us with DTN. And so this is kind of the outline of my lofty goals to start pushing this high rate DTN and get it truly integrated into the NASA SCAN, that is Space Communication Navigation Service portfolio. So that's kind of the first half, and then there's kind of a second half, a structural break in the presentation. So I'm trying to go quickly and also clearly at the same time somehow. Maybe I'll just ask, are there any pressing questions at this point?
I see one question in the chat, which is
Once, going twice.
Can you hear me?
Yes.
Jorge Amadeo asks, the LCRD test launching, is
Yes.
there a launch coming up in 2023?
A launch?
Yeah.
For LCRD?
Yeah.
LCRD already launched, and Illuma-T will be, maybe you're thinking Illuma-T is supposed to launch in February of 2023.
Okay, good. That makes it clear.
Yeah, it's like in here, the LCRD satellite is up, checked out, and we're actually hoping to start running these DTN tests that I've been kind of alluding to towards the end of this calendar year in preparation for Illuma-T testing, which will probably happen in the middle of the next calendar year. So that's kind of the timeline we're looking at.
Okay, great. And two more things. One, Oscar Garcia remarks that the IPN-SIG pilot project working group has been doing DTN integration with cloud infrastructure for a couple of years, and would be happy to work with you on the implementation. And also, Carlo Caini asks if you've tested interoperability between HDTN and the ION implementation.
Okay, so yeah, excellent. These are all good questions before the next half, which I'll try to go quickly through, I promise. So I definitely welcome all collaboration. I'm completely disinterested in any kind of artificial boundaries and barriers that would keep us from moving things forward. The other thing is, yeah, the interoperability has been tested for V6 and V7 between HDTN, DTNME, and HDTN. So,
oh, but not with ION then.
And with ION, yeah.
Oh,
and
okay.
with ION.
That was the question.
The only thing is that HDTN can source and sync tens to hundreds of thousands of bundles per second. And so you might wind up running TC or QDisk or something like that to do the right shaping and so forth to make sure that the different implementations don't overwrite each other. Because one thing you got to keep in mind is that there's different implementations for different implementation scenarios and specifics.
Sure.
So there's a little bit of alignment that needs to happen, but absolutely, as far as formats and everything go, they work.
Do you have time for one more question before you start your second half?
Yes, if it's brief.
This is, I don't know if it's brief. Juan asks about using DTN. Is it also being used to overcome disruptions that result from there being clouds that interrupt the optical link from the ground? And is that a different challenge than scheduled disruptions the way you have in the rest of the interplanetary internet?
That's a longer discussion. I guess what I would say is that if you know something about the link that's going to happen, you would choose your convergence layers and underlying protocols accordingly. And that might include, say, LTP or something like that, but it might also include something lower layer where if you have momentary disruptions from clouds, you would try to low pass filter that stuff out with, say, interleavers, which is actually where the 4-second round trip time to geo for LCRD comes from. And then for things that don't happen on the 1 or 2 second level, then you would try to start to get reliability from that on the network level, either in transport or bundle, depending on what's going on. But I think that there's a lot of trade-offs in understanding what the inflection points are between the various layers and when one should kick in and the other one should assume that things are taken off could definitely be researched further.
Okay, a good topic to pursue, but why don't you go ahead now?
All right. So I can't leave the research side behind. Of course, some of the things that we need to do really do come down to building things and implementing them. There's also things that just need to be better understood. The generalization from internet to solar system internet is truly vast. And so I've been keeping that alive. I think I'm beyond 70 students at this point. And with my student armies, we've been able to do a good bit of research. And I'll try to blow through this as quickly as I can. This is a model, this is a graph of the entire internet. I like it simply because we talk about models, we talk about theory, and the theoretical underpinnings are what support and give rise to everything from routing to what you might just call user experience. And as we gain this this foundation that lends itself to something computational, then we can start to look for scalability and more scalable approaches to things like a solar system internet. And of course, with the rate at which we're launching things into space these days, this becomes more and more pressing. So this is something that we've spent a lot of time looking at. Of course, with the regular old internet or with more static, at least more static by comparison networks, we look at graphs. So one of the things that we've done a lot of work is trying to understand how to model temporal graphs and temporal networks. I'm going to kind of give high-level overviews of all this stuff, and then I'll just kind of invite people to either read papers or contact me. But I guess what I want to share with the world is that we have a strong effort looking into such things as the nature of temporal graphs and how familiar algorithms, such as Dijkstra, might fit on top of them. One of the other things that we can do with these temporal networks is it turns out you can actually generalize familiar notions of curvature to these things. And so I have curved services up atop and graph theoretic versions below. And just as curvature governs flow on a smooth surface like a manifold, it also governs flow in networks in a very quantifiable way. So this is a way to start modeling diffusion of information which especially has applications for link state announcements and other things that I'll get to in a bit. So I'm excited about this. One thing you might think is EIGRP as something that might take a real number, which would be curvature, to make route computations. So we have an upcoming paper on that. One of the other things that we've done is we've found new ways to model familiar things like Dijkstra, such that we can take network areas or autonomous systems or things of this nature and start applying them to DTN. So maybe you don't have end-to-end knowledge of what your network looks like, but if G1, G2, and G3 at least know about themselves and the overlaps with these other networks, we can still find a path from the left to the right. And so we now have a mathematical model for how to glue DTNs together. And it actually turns out that part of the way this works is we can start to build these ordered pairs of information that start to look a little bit like addressing. And while it's not quite addressing yet, it does give us formal separations between the areas in a way that the message basically passes as it moves through the network and brings with it. And so you can start to perform these local optimizations in the networks, or at least in the network areas that you know something about, and start moving around where global optimization may be impossible, which one would expect. And so my immediate application of this would be to join multiple discovery-based areas with, say, CGR-based areas. So I'm pretty excited about this. One of the other things we've done is we've started to bring hypergraphs into the mix. Hypergraphs are like graphs, except edges might connect multiple nodes. The most obvious example of this, I think, would be like a radio tower talking to multiple cars. It doesn't make sense to have individual edges, but maybe have one giant edge. It turns out that it is known that this is the proper and better way to model networks with broadcast, multicast, whatever cast types of communications. So we're now bringing this to bear on DTNs. Rather than reading the text, I'll just give this type of suggestive graph where you can sort of see we have a hypergraph with 4 hyperedges. And if we're trying to get from Earth to Mars, we can start to find paths within hypergraphs. And again, it turns out that from an optimality standpoint, this is the improved approach. So I'm happy that these new tools are being applied. It turns out there's a lot of active research from many different organizations in the hypergraphs, especially for communication. So it also creates better overlap with everything from NIST to the Pacific Northwest National Labs and even greater academic collaboration. And then the other thing, I'm not going to read this to you. We asked an AI to draw time synchronization in a delay tolerant network, and that's what it looked like. But we have the first set of like a true mathematical foundation for time synchronization in DTNs. So rather than assuming that time sync has happened, can we start thinking about time sync as a service in a space network where perhaps you do have network segments or areas that don't see GPS or something like that. So we're happy about a lot of this progress here. And as far as moving forward, we've gotten several invitations to start working with our academic partners and NIST and PNNL, so people have taken note. And I would like to conclude by thanking this year's intern team, because without them, I would not have been able to do any of the fun research, and I would have done nothing but project management the whole year. So hopefully this wasn't too over time. And if there is time for questions talking about research or whatever, I am happy to take them.
Thank you, Alan. You are well under time. We've got another 5 minutes here.
Awesome.
Stuart Card has I'm unclear on whether it's a question or not, but he says to show all the information needed to make routing decisions, these are directed, labeled, weighted hyper multigraphs.
Yeah, they would be. That is correct. In the end, they would definitely have all that information and actually more. So we would use that information to support additional data structures on top of them, which would be used for routing within some kind of area.
Oh, okay, and let me also ask if there are, where can people find links to all of this research? Do you want to post them in the chat, or do you have a single website that people could go to, something like that?
I've been hoping to get a lot of this just posted on the DTN website. So the research that happened this year is going to be presented at the IEEE Aerospace Conference in Montana in March. And those papers are due on Friday. So that's pretty, that's coming up.
Yep.
And so I'll put the titles of those papers. So if people are interested when they're complete, just email me, or maybe I'll see you at the IEEE Aerospace. And then I can put some links to papers that were published this year that kind of bring you up to speed.
Great.
And so I try to combine a mathematical and also a practical approach. It turns out they're not mutually exclusive after all. And so the papers are a bit mathy, but if you're not allergic or if you want to talk about it, yeah, by all means, reach out to me. I'd be thrilled to talk your ear off about it.
And when you say the DTN website, do you mean NASA's DTN website? Okay. Do you happen to have that URL handy? I will type it in here.
I don't, because I haven't been able to get the papers up on it yet.
Okay.
I think right now we're ignoring each other because they won't get my papers up, but then I haven't talked to them. It's half my fault.
All right. So people who are interested in pursuing this, NASA has kind of a lot of information on DTN. And if you do a Google search for NASA DTN, you'll see more than you can possibly read in a week, I think. And these papers will find their way up there as well.
Yeah, they will. Yeah.
And thank you very much. Nadia has posted this link, grcnasa.gov space/scan/ACS/tech-studies/DTN publications. Oh, this is for DTN, HDTN in particular.
I don't, Nadia, do you know if those include the aerospace conference papers from this year?
That includes the flight test one.
Oh, the flight test one. Okay. Yeah, I'll post some links to the other ones. There is a quiz on Friday.
Yeah. Yeah. Okay, that brings us pretty close to the end of the hour. Any last minute questions? Going once? Going twice? I will turn this over to Juan to finish up. Thank you.
All right. Thanks, everybody. I'll put myself back on mute where I belong here.
All right, guys. So there is nothing else for the rest of the day. Thank you, everyone, for joining. As I said, this will be recorded. It is being recorded and will be shared afterwards. So I just leave the message that we will have another session tomorrow at the same time that today. We'll host David Evans, ESA's OPSAT managing operator. So some interesting discussion about how the satellite supported some DTN experiments recently. Some other expert talks available in the website. So without further ado, thank you guys for joining. Yes, hope to see you tomorrow.
Thank you.
Cheers.
Thank you.